Richard Feynman's Mental Models: How to Think, Learn, and Problem Solve Like a Nobel Prize-winning Polymath, written by Peter Hollins, narrated by Russell Newton. Keep your eyes wide open. Approach everything with circumspection. Don't accept any truth without deep thought. Expose and eradicate half-truths and demagoguery. Learn to wonder at the beauty of the world around you and, above all, think about everything. Richard Feynman. What do you know? How do you know the things you know? Could there be a better way to know? And how could you find it out? What don't you know, and how might you learn? Could you be wrong, and what would that look like? What is, and what faculties do you have to perceive and understand it? These are the sorts of questions that most of us seldom get around to asking. Epistemology is the field of inquiry that asks about inquiry itself, and questions the limits, characteristics, and sources of our knowledge. Being able to think about how we are thinking and know more about the process of accumulating knowledge about the world requires a mindset shift all its own. Nobel Prize-winning theoretical physicist Richard Feynman is one of the best-known and most loved scientists of our time. He was involved in the development of the atomic bomb and did pioneering work in nanotechnology, superfluidity, and quantum computing. What made Feynman so relatable, however, was his ability to popularize his work, and his many books and autobiographies captured the public imagination and earned him a legacy in the public eye as the face of intellectual rigor, scientific progress, and the powers of the rational mind. But there's not some special access to reality that is afforded to theoretical physicists alone. What made Feynman's mindset and worldview so compelling was how he thought, not what he thought. In other words, he was consistently led to ask himself about what he knew, how he knew it, and how he could do better and learn more. This is precisely what this book is about. Using the inimitable Feynman as our guide and inspiration, we will peer beyond the realm of physics and engage with the underlying nature of inquiry itself, and how we might become students of life in the very broadest sense. Whatever your vocation, skill set, expertise, special interest, or personal challenges, your life can be improved by learning to learn. No matter if you are primarily concerned with personal relationships, your occupation, your life path in general, or the grand, overarching philosophical questions that have teased and taunted even the greatest minds, you cannot help but improve your situation by fine-tuning those intellectual faculties that have the sole job of orienting you in the universe and helping you make sense of it. Consider this fine-tuning process a kind of meta-skill that is transferable to any area of life. Learn how to observe, to synthesize information, to analyze, to create, to solve problems, to extract meaning, to ask questions and seek their answers. In other words, learning to think. And you will master yourself and your world to whatever extent is possible for a human being. The ability to really think, and we'll soon see how most of us have a complete misunderstanding of what thinking is, will never go out of fashion or lose its value. Your brain is a tool that will inspire the elevated use of every other tool you encounter. It's the kind of tool that possesses a fascinating potential, the ability to change and adapt itself as needed. Like the physicists who have learned to operate at the very vanguard of human comprehension, you too will be able to ask, what do I have to be? And how ought I to think to understand this? Think like a Martian. In an interview, Feynman once shared a game that his father had taught him as a child. They'd sit at the dinner table, engrossed in discussion of a topic, and his father would playfully ask something like, "Suppose we were Martians who had come to the Earth for the first time and were looking at things from the outside, having never seen them before. What would that be like? What would we see?" On the one hand, this is a simple child's fancy, but on the other, it captures the spirit of scientific inquiry. It's a game that asks us what radically curious perception would look like, with zero preconceptions. What would the world look like to you if you had no pre-existing beliefs about it, no biases, no prior understanding to cloud your observations? It's a question that gets deeper and deeper the more you think about it. With fresh eyes, everything would start to look wildly interesting. You would take nothing for granted. For example, being a Martian, let's suppose you never slept and had no need for it. You don't know what sleep was and have never even imagined it before. It was not only not part of your world, it wasn't even something you acknowledged as being strange or impossible. Now imagine you came to Earth and observed that within every 24-hour cycle, human beings of every kind would fall into a period of unconsciousness, and they'd close their eyes and grow still and lie horizontal, their breathing slowing. You'd notice they'd get into big pouches made out of foam and layers of fabric, roughly the same size as their bodies, and stay there for a handful of hours. Now, if you were a scientist Martian, you would have a load of questions. Where would you even start? You'd wonder what was happening and why. You'd be curious about what it felt like to suddenly lose consciousness this way, and what purpose it was serving, and what it meant that humans seemed to vary in their practice of this habit. You'd wonder what their experience was like. What does it actually mean to be awake? Does your brain still work? Does your consciousness go off all at once, or does it happen gradually? Why? For a Martian who only knows one state of being, wakefulness, thinking about the idea of sleep must be like human beings imagining some other third state of consciousness in addition to sleep and wakefulness. You started with something completely arbitrary, obvious, and kind of boring, sleep. You were grappling with very deep questions of what it means to be conscious, how we can actually know what another person's consciousness feels like, and what we're really talking about when we use an everyday word like awake or aware. Now, such questions can be fun if they inspire a renewed appreciation for the strangeness of life, and can certainly be good starting points for writing science fiction, but let's go deeper. Feynman gave an analogy where he described the process of seeing a bird in a tree. Someone might ask you what bird it is, and you could give its name. Now, does that mean you know what the bird is? Do you really grasp the meaning of what is in front of you? And can you say you have knowledge of it? Consider that the name you give will be in your language. You say the bird is a lark, but an Italian speaker will say it's an aladola, and a Greek speaker will say it's a cordalos, and a Hindi speaker will say something else. Maybe a Martian comes down, and when asked what he sees, blows air bubbles out a little funnel on his head. You get the picture. Knowing the arbitrary symbols assigned to a thing is not knowing it. Recognizing certain patterns and features and mapping them onto pre-existing mental models is, in a way, the opposite of really knowing it. Have you ever really seen a bird? Look again. What do you really see? Imagine you have never been told anything about birds and have stumbled brand new with a fresh and unused brain into the world. There's a phenomenon unfolding in front of you, a kind of movement of light, a noise, a being. What is it? So, if you were the Martian observing Earth people sleeping, go a step deeper and imagine that you have no idea what consciousness is and no pre-existing beliefs about this thing called the mind. After all, if someone were to ask you right now, what is the mind? Do you think you could easily explain it to them if they didn't already know? The Martian question is a powerful tool for getting beyond the limits of our language. Sometimes we think of learning as an accumulative process, that we're ignorant, then we pile knowledge on top of that ignorance, adding to our understanding. But in many ways, really grasping the nature of reality is just as much about taking away. By peeling back the layers of assumption, we clear our perception and look at things afresh. The biggest impediment to understanding the world as it is, then, is the insistence that we already know what it is. We see someone lose consciousness in a pouch made of foam and fabric, and we confidently say, "She's gone to bed." The language gives the impression we have a more comprehensive understanding of what has occurred. But do we? When you ask the Martian questions and try on a fresh perspective on things you think you already understand, you change the kind of questions you ask, and that means you change the kind of answers you expose yourself to, and therefore the kinds of solutions you can dream up. You think outside the box because you're able to see that there is a box in the first place, and you become curious about who put it there and why, and what it would mean if it didn't exist anymore. The Martian question in real life. This might seem great if you're a children's author or a prize-winning physicist, but can it really be applied to real life? Do you have to reinvent the wheel every time you want to make toast for breakfast? Consider the example of inventor Martin Cooper, the man who's credited with being the grandfather of the mobile phone. He didn't just create a fun new gadget. He looked at the world of telephone communication as it was in the early 1970s and asked the question, why do you have to always call a place? Why can't you call a person? You see, his shift in perspective was the very idea that you could detach the ability to make telephone calls from any particular place. It seems obvious to us today, but it wasn't back then. He pioneered the idea of a phone as a personal thing, saying he wanted to create a personal telephone, something that would represent an individual, so you could assign a number, not to a place, not to a desk, not to a home, but to a person. Martin Cooper asked interesting questions, not because he was an intelligent inventor and engineer or an expert in the field of communications, he was both those things, but because he was able to look at the situation with fresh eyes. The question that defined his career, and arguably the era of mobile devices, was the kind of question a 5-year-old might ask. Today, we don't think of this leap of imagination as anything all that special, since it has become part of our world. In the same way, we don't look around and see the vast potential for ideas that we simply have not had the insight to ask about until now. They're there, though, hiding in plain sight, just beyond the same kind of simple, even obvious question that Martin Cooper asked himself. Get in the habit of asking these kinds of questions yourself. What would this situation look like to me if I knew nothing at all about it? What assumptions, expectations, and foregone conclusions am I taking for granted? What if I remove those? How might my life look to a complete outsider, to someone from a different planet, a different country, a different historical period? What about a younger or older version of myself? When I answer a question with a term or label, do I actually know what this word means? What is interesting here? Could it be some other way? Feynman's advice, play more. One of the themes we'll return to again and again in this book is that of intellectual newness, freshness, and lack of preconception. This childlike state of mind is not just a metaphor. Children are, in many ways, the natural experts of learning, since that is precisely what their brains are designed to do. Sadly, we lose this knack for plain perception, curiosity, and joy as we grow older, and are taught that learning is not about new things, but about old, dusty, tired things. When left to their own devices, children don't learn by forcing themselves to sit in structured lessons and making a big deal out of unpleasant, boring, and deadly serious school, which is somehow separate from the rest of life. Rather, they play constantly, and in their play, they learn vast amounts about the world they inhabit. Feynman is said to have come up with his Nobel Prize-winning idea by watching students spin plates in a cafeteria in Cornell University, where he worked at the time. Finding a solution to a physics question is something as mundane as tossing plates around in a cafeteria, which tells you just how powerful playful curiosity can be. According to Feynman, physics disgusts me a little bit now, but I used to enjoy doing physics. Why did I enjoy it? I used to play with it. I used to do whatever I felt like doing. It didn't have to do with whether it was important for the development of nuclear physics, but whether it was interesting and amusing for me to play with. When I was in high school, I'd see water running out of a faucet, growing narrower, and wonder if I could figure out what determines that curve. I found it was rather easy to do. I didn't have to do it. It wasn't important for the future of science. Somebody else had already done it. That didn't make any difference. I'd invent things and play with things for my own entertainment. So I got this new attitude. Now that I'm burned out and I'll never accomplish anything, I've got this nice position at the university teaching classes which I rather enjoy. And just like I read the Arabian Nights for pleasure, I'm going to play with physics whenever I want to without worrying about any importance whatsoever. Within a week, I was in the cafeteria and some guy fooling around throws a plate in the air. As the plate went up in the air, I saw it wobble. And I noticed the red medallion of Cornell on the plate going around. It was pretty obvious to me that the medallion went around faster than the wobbling. I had nothing to do, so I start to figure out the motion of the rotating plate. I discovered that when the angle is very slight, the medallion rotates twice as fast as the wobble rate. Then I thought, is there some way I can see in a more fundamental way by looking at the forces or the dynamics? I don't remember how I did it, but I ultimately worked out what the motion of the mass particles is and how all the accelerations balance. I still remember going to Hans Bethe and saying, "Hey, Hans, I noticed something interesting. Here, the plate goes around so. And the reason it's 2-to-1 is," and I showed him the accelerations. He said, "Feynman, that's pretty interesting. But what's the importance of it? Why are you doing it?" I said, "There's no importance whatsoever. I'm just doing it for the fun of it." The diagrams and the whole business that I got the Nobel Prize for came from that piddling around with the wobbling plate. Relaxation, daydreaming, creativity, and, yes, fun are not impediments to serious intellectual activity. They're an important part of it. Your mind is naturally curious about the world. Curiosity and playfulness are a big part of how it survives and evolves. But who taught us that this survival necessarily has to be a boring, difficult thing? Where did we learn that the real living of life happens only when we're working and working hard, and that play and joy and curiosity are only recreation and don't count for much? Now, before we go further, it's worth saying that Feynman's sentiments about serious play are not about being lazy, uncoordinated, or simply sitting and waiting for a fully formed prize to fall into your lap. There is certainly a time and place for deep work, effort, and pushing through challenges to grow our abilities. Feynman believed then that it was a balance. Work hard, then let go, then work hard again. Think of it a little like a muscle growing stronger. It's essential to challenge the muscle to work hard, but it's also essential to rest, or just to spontaneously let the body sometimes do what it feels is best, maybe dancing. Many of us who are ambitious and or have been indoctrinated into the ideology of all work and no play will find it difficult to let go. Learning to trust ourselves to be spontaneous, relaxed, and joyful can take some practice. If you're someone who is suspicious of Feynman's play more advice and want to know exactly what makes it different from being a lazy bum, then consider the following. Serious play still requires domain knowledge. Watching the spin and angle of rotating plates is great and all, but you'll notice that Feynman had a hefty dose of pre-existing domain knowledge, and so his question about why the plates moved as they did could be answered with the skill set he already possessed. Perhaps if he'd been a musician, he might have used that knowledge to explore the concept of spin a little differently. Just because play is important, it doesn't mean it's not worth working really hard to fill up your intellectual inventory with tools, concepts, ideas, theories, and skills. When you have a burning question and are genuinely curious about something, then you can whip out these tools and use them all the better if you're very comfortable with using them already. Pablo Picasso was often accused of not being a real painter, since it appeared that his more famous works could be created by anyone without any artistic talent or technique. But look at some of his earlier paintings and you'll see that the modern artist knew all the conventional rules of painting and was indeed a very competent and accomplished painter before he broke them. Feynman, too, had to be fully versed in the conventions of his field before he started to question them or make his own contributions. Serious play is still focused. There is value in rest and recuperation. The composer Bach often had inspiration strike him while he was not at work, but outside, walking in nature, letting his intellect relax and loosen. Serious play, however, is not the same as relaxation. It is not distracted and scattered. Rather, it is deeply, deeply focused on one task. Watch a child as they play and you'll see this focus. They have seemingly infinite energy, patience, and attention for a task they're engrossed in. Replicate this by spending as much time as you can on the things you're interested in. Don't expect world-changing insights and paradigm shifts for something you do half-heartedly or for a few minutes once a week. For Feynman, everything in his life was physics. Even within the field, he focused on those areas he was most interested in. He might not have been as effective if he had tried to apply himself over many disparate fields at the same time. Serious play has a purpose. When we're killing time or just seeking mindless entertainment, it's not the same as serious play. This kind of activity is open-ended, curious, and joyful, but it also has a definite point. It's not a free-for-all. Feynman was just itching to understand why the plates behaved as they did. He was attacking the problem as though it were a game, but definitely one in which he was trying to win, trying to solve the puzzle. Try to be purposeful in the same way. A little healthy obsession is a powerful thing. An unexpected cure for burnout. Granted, most of us don't want to completely upend the paradigm we're working in, invent the next big thing, or be breakout disruptors who leave a big mark on the world. If you do, though, great. Learning to play more and mastering the kind of serious play that Feynman spoke about is not just a way to create or solve problems. In Feynman's own example, he describes how returning to a childlike sense of wonder and interest was how he broke through a growing sense of boredom and dullness in his work. In other words, it was only when he could reconnect to curious and engaged play that he broke out of a rut and made real progress. Not incidentally in his office, but while on a break in a cafeteria. It would be no exaggeration to say that post-pandemic, the world is burnt out. Whether you're an entrepreneur or work for someone else, there's a strong chance you've experienced exhaustion and lack of motivation. It's no coincidence that messing around with plate rotation in the cafeteria just for fun is what actually led to one of Feynman's greatest contributions. He was able to work beyond his previous limits because he'd allowed himself to play. If you are tired, unmotivated, or even bored, it may be time for serious play to breathe some life into your world. You need a fresh perspective and the energy that comes with genuinely being excited and curious about something. If you are legitimately fascinated and having fun answering a question, then you are instantly tapped into a source of energy and power that can never be rivaled by any other incentive. Feynman didn't care when fellow scientists asked him what on earth he was doing and what the point of it was. That's because he was driven from within, because it was fun. Try to play with your work again. Whatever you want to, in whatever direction you want to. Give yourself permission to follow trivial observations and ask questions, even if they are useless ones to ask. Creative play can soothe stress, make you more resilient, and help you focus longer. Too many of us appreciate the value of hard work, but completely undervalue our own energy, excitement, and pleasure. Here are a few examples to show what that might look like, even if you're not a physics genius. You're learning the piano but getting demotivated and bored, so you make sure that a few times every week, unscheduled, you just sit down at the piano and do what you want. It's not about working through the pieces your teacher has assigned you or ticking off a list of scale exercises. It's just about you playing around with the instrument. You don't know what you'll do until you try it. When something piques your interest, you follow that feeling of pleasure and excitement. You notice that even though it feels a bit awkward at first, you enjoy these sessions the most and always end up playing for longer than you thought you would. You're trying to write a novel, but continually hitting creative blocks and finding yourself procrastinating. You decide to start every planned writing session with a crazy, out-of-the-box game, whatever you feel like. You write crazy dialogues between the characters and envision them as Punch and Judy puppets. You put 5 minutes on a stopwatch and see what happens when you write continuously without thinking about it. Or it seems like it would be fun to deliberately try to write a really awful book just because it would be funny and you want to try it. Your job as a nurse is exhausting and unrewarding. You're close to giving up and feel desperately sad to have lost what you thought was your life's calling. So you take all the pressure off yourself, quit your job, and start volunteering at an old folks' home instead. Money's tight, and you still have to figure out what job you'll do next, but slowly, by working more on your own terms, you reconnect with what made you fall in love with nursing in the first place. Your energy stores fill up again. You remember your vocation and passion. When it comes time to apply for new jobs, your mindset has completely changed, and you find yourself accepting a completely different role from the one you always thought you wanted. Burnout is complex, and the world of work is complicated. Not all of us have as much opportunity to rest, recuperate, and play as we'd like. Nevertheless, if you are feeling flat about your work, uninspired, or plain old bored, then rest assured that there is always a source of energy and motivation you can tap into. It's called the joy of curiosity, and play will teach you how to find it and how to re-energize yourself. The scientific method, according to Feynman. Learning to see the world as a scientist sees it requires 1, the presence of mind to suspend everything you already think you know, and 2, being able to look at what you really observe with a sense of childlike playfulness, joy, and deep curiosity. These are not methods so much as mindsets. However, when a certain mindset becomes natural for you, you can't help but develop a method for how you tend to approach the project of learning, understanding, and making meaning. This curiosity and open-mindedness is in fact the birthplace of what is arguably one of mankind's best inventions, the scientific method. First thing to know about the scientific method is that it's not really about science. Rather, it's a way to structure our thinking and our approach to observation, gathering data, making predictions and theories, and inching our way closer to truth and understanding using reason and empiricism. Physicist Brian Cox once spoke to students at Manchester University about black holes and showed them a video clip from a 1960s lecture by Richard Feynman. Cox introduced the clip by saying it was simply the best explanation he had yet encountered about the spirit of science and what the scientific method was all about. The clip easily laid it all out in under a minute. According to Feynman, now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then, we compute the consequences of the guess to see if this law we guess is right, what it would imply, and then we compare the computation results to nature, or we compare the experiment or experience, or capture it directly with observations to see if it works. If it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't make any difference how beautiful your guess is. It doesn't matter how smart you are who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it. You can probably see why Feynman was regarded as such a charismatic teacher and communicator. Let's look at what he's really saying about the scientific method. Step 1. To look for a new law, first, guess it. Step 2. Compute the consequences of the guess. Step 3. Compare the computation results to nature. Step 4. If the results disagree with nature, then our guess is wrong. Step 5. Repeat. Optional. So, the scientific method is nothing more complicated than making a guess about reality and observing reality in many different ways. And if our observations don't support what we observe, we can say something about our guess. That is, it wasn't right. If what we guess about reality turns out to match what we observe, say in experimentation, then we have reason to believe that our guess holds some water. We continue asking questions, making observations, and designing ways to test whatever we guess next. In more formal scientific terms, the guess Feynman is talking about is a hypothesis. It can be based on what we already know or what we have observed. It can emerge because there are obvious gaps in what we know, or it can be driven by nothing more than curiosity. For published academics, the name of the game is to look for hypotheses that are relevant and original. But luckily for you, as a layperson, you're not beholden to such limits. You can ask whatever question you like, bearing in mind that making a hypothesis is just a way to ask reality a question. Imagine that reality is a little like one of those magic 8 balls that can be shaken to reveal an answer to a question. Let's say that this magic 8 ball only has 3 possible responses to any questions you ask. It can say yes, no, or try again. The try again response could mean a few things. Your question is phrased incorrectly, there's been an error along the way, or you need to, try again. Your guess might be true, it might be false, it might be both. It might be neither. When you ask a question of this great universal magic 8 ball, then you cannot ask it, why do some people not die of this virus that's killing everyone? Or, what medicine will help people infected with this virus? The ball will only tell you that any one guess is correct, incorrect, or undecided. You could ask, do the people who survive this virus have higher serum bilirubin levels than those who don't? Now, this asking can take the form of an experiment. You set up a research design where you get 3 groups: people who have died from the virus, people who have the virus but have not died from it, and people who have not had the virus. You then look at the blood work of all three groups and ask what their serum bilirubin levels are. Since you have thousands of people to measure and observe, you use statistics to help you crunch the numbers. You put everything together and notice a pattern. The people who have the virus but are not dead do indeed have higher bilirubin levels than both of the other groups. The result is essentially the magic 8-ball saying, yes, this is a pretty good guess. But that doesn't mean that that's the end of the story and we have conclusively proven something forever. It just means we've discovered some evidence and support for our guess. When it comes to hypotheses, scientists always frame their questions so they can be disproven. For example, they make a claim. Bilirubin protects people from the virus. And they set up an experiment so they can observe if this guess matches up with what really happens in the world. Either they conclusively prove the statement false, or they find tentative evidence that it might be true. So we seek to find out whether a hypothesis, a guess, can be rejected or not. We advance in our knowledge about the world, in other words, by ruling out what definitely isn't true, with the goal of gradually and by degree approaching what is true. We begin with speculation, and putting that speculation out into the real world, we see how it performs. Then, based on our results, we can make another experiment, and our next guesses and speculations can be a little smarter than the previous one. Naturally, real experimental science has strict protocols to follow, and its own logical rules that help formalize this process. Scientists have a whole range of activities that count as observation, and there is a difference between theoretical and applied sciences, between different kinds of observations, for example, in the social sciences versus medicine, and between different approaches that use tools like mathematics, statistics, software, or technology to extend and expand the normal powers of human perception. But in the end, it all comes down to Feynman's basic recipe. Make a guess, observe what reality is actually doing, compare the two, rinse and repeat. Another important thing to remember, and Feynman does approach this in his simplified explanation, is that there is no ego in the scientific method. If we make a guess that turns out to not explain reality in the way we thought it might, this isn't a problem. We haven't made a mistake. And that doesn't mean we're bad or wrong or stupid. Making wrong guesses is doing science in the exact same way that making right guesses is. They both take us closer to the truth, and therefore they both have value. In the same way, a guess is right because that's what it is, not because it's been made by someone who is good or intelligent or has been right before. A guess can be right and still be something we don't like, and vice versa. Finally, a true scientist asks a question for one reason and one reason only. They want to know the answer. They don't ask it because they want to confirm that what they already believe is true. They're not looking for proof that will permit them to continue holding on to what they suspected was the case all along. Their first duty is to find something that is true and correct. If the process that leads them there entails dozens of wrong guesses, then so be it. If human beings were doing science in this way, you would expect them to regularly publish findings in which their hypotheses were shown to be rejected by their observations and experiments. In reality, though, academic publishing contains an improbably high level of papers showing that the researcher's guess just so happened to be correct. In 2005, John Ioannidis, a professor at Stanford School of Medicine, argued that the majority of papers published in medical journals were likely false positives, that is, found evidence where there was none and could not be replicated. The way the researchers were using hypothesis testing and processing their results statistically meant they tended to get exactly the kind of response that was most desired, i.e., support for their hypothesis. In academia, there is considerable pressure to produce a certain kind of knowledge in certain high-profile and lucrative research domains, and the Great Replication Crisis showed just what happens when we seek to find evidence for what we want to believe is true, rather than asking outright what is true. Questionable research practices, publish or perish culture in universities, political pressure, and the rampant misuse of statistics are all impediments to what Feynman would have considered truly scientific. But that doesn't mean the principle itself is not sound. On a smaller scale, we are all at risk, as flawed human beings, of succumbing to our blind spots, biases, prejudices, and pet theories. We can convince ourselves we're encountering truth when we're really just creating something we like and naming it truth because it's convenient. Let's zoom out and consider an example from the non-scientific, non-academic, everyday realm. Let's say your car's acting up. You don't know much about cars, but it's been making a weird noise, and one day you see a light on the dashboard, one you don't recognize, with some weird circles and a cross through them. You look in the car's manual to see what the symbol means. It says brake lights. But what does that mean? Your hypothesis? The brake light is broken. How do you test this hypothesis? You could step outside of the car and look with your own two eyes. But then you see something curious. Both brake lights appear to be working. Okay, time for a new hypothesis. The brake light is itself broken. Now, how are you going to test that? And how can you determine whether this phenomenon is connected with the noise you're hearing? The next day, you notice two things. The brake light is off, and the noise has stopped. Now, this does offer some support for the idea that the light and noise are somehow connected, but you haven't proven it yet. If you're not a mechanic and can't get to one, you might simply conduct an experiment that consists in you noticing whether the two phenomena ever occur together. Every time they do, you gather more evidence for the idea that something is going on, and these two events have something to do with it. When one day the noise occurs without the light being on, you reason that they could in fact be two independent phenomena. Sometimes the spirit of the scientific method simply reveals itself in our ability to stop ourselves from saying, "It can't be done," so we can instead actively ask, "Can it be done? How can it be done?" Or even better, what is being done right now? What do I observe, and why is it happening? The scientifically minded person has an attitude of experiment. They don't make pronouncements and leave it at that. They frequently think, "I wonder what will happen if I..." and follow through. If something is unanswered, mysterious, or unknown, they don't shrug their shoulders or choose the answer they like best and cling to it. They say to themselves, "Let's find out." While such examples of trial and error and logical common sense seem almost too obvious, the fact is that we cannot really arrive at knowledge and understanding by any other way. The same applies to things outside the five senses. In CBT, cognitive behavioral therapy, counselors often advise people to test their theories of reality rather than just assume that their knee-jerk interpretation of events is always correct. If someone frowns at you on public transport, you could quickly conclude that you're weird and unlovable, and everyone knows it. Or you could seek the most likely explanation that requires the least number of assumptions. The person was unhappy for some other reason that has nothing to do with you. But you don't necessarily have to go on faith. You can test your unlovable hypothesis the next time you go on public transport. Is what you observe in line with your theory? In other words, Is everyone you encounter frowning at you or behaving as though they dislike you? If people are just minding their own business and being perfectly neutral about your presence, you can safely conclude that your original hypothesis was just plain wrong. Remember what Feynman said: it doesn't make any difference how beautiful your guess is. It doesn't matter how smart you are who made the guess, or what his name is. If it disagrees with the experiment, it's wrong. That's all there is to it. In our example, it doesn't matter how right your hypothesis feels, or how much your guess seems like it fits your pre-existing worldview. That is, the one in which you are pretty sure you're unlovable. It doesn't matter how right you want to be. If observation doesn't align with reality, then your guess about reality is wrong, and that's all there is to it. Summary. Feynman was a brilliant scientist because of how he thought, not what he thought. Whatever your vocation, skill set, expertise, special interest, or personal challenges, your life can be improved by learning to learn. To see the world anew and without stale old misconceptions, try to look at it as though you were a Martian arriving on Earth for the very first time. What do you see? What would the world look like to you if you had no pre-existing beliefs about it, no biases, no prior understanding to cloud your observations? Knowing the arbitrary symbols assigned to a thing is not knowing it. Look beyond language. Relaxation, daydreaming, creativity, and fun are not impediments to serious intellectual activity, but an important part of it. Your mind is naturally curious about the world. Curiosity and playfulness is a big part of how it survives and evolves. Work hard, let go, then work hard again. Serious play still requires domain knowledge and is focused and purposeful. Burnout can be helped by this kind of play. The scientific method is a way to structure our thinking and our approach to observation, gathering data, making predictions and theories, and inching our way closer to truth and understanding using reason and empiricism. First, make a guess about a new law. Then compute the consequences of the guess. Then compare the computation results to nature. If the results disagree with nature, then your guess is wrong. If they agree, you have support for your hypothesis. What you want to be true is irrelevant. A scientist asks a question because they want to know the answer, not because they want to confirm what they already believe is true. This has been Richard Feynman's Mental Models: How to Think, Learn, and Problem Solve Like a Nobel Prize-winning Polymath, written by Peter Hollins, narrated by Russell Newton. Copyright 2023 by Peter Hollins. Production copyright by Peter Hollins.